pleasure to be able to introduce our special speaker for the evening. I've watched Sara Seager from when she was a high school student, coming into the Toronto Centre meetings and then going to U of T. Do you still have the U of T jacket? Got rid of that a long time ago, eh? I do remember on Friday nights, she'd always show up wearing one of the U of T leather jackets to the meetings down at the planetarium. And over the years, she's risen through the academic ranks, and now she's a professor at Massachusetts Institute of Technology and a MacArthur Scholar, and has a whole passel of awards and recognitions. And I think as an honorary member of the RASC and a member of the Toronto Centre, we can all be very proud of her accomplishments over the years. Tonight, she's going to speak to us about TESS and the search for more exoplanets. So,
thank you.
Sara, welcome.
Thanks, Ralph. Thanks, everyone. It's always great to be back here, and thanks for that welcome. In fact, I got my start in the RASC when I was even younger than Arushi, when my dad took me to a star party where I don't know if it was any of you here, but had telescopes out, and I remember seeing the moon, and it was spectacular. We weren't a maker family; it was more like armchair observing, but it was still how I got involved. And as Ralph was saying, as a teenager, I was able to join on my own because my family lived in Toronto in the South Annex. So I could walk or ride my bike to the planetarium, and I religiously went the meetings were every other Friday. Actually, they might have even been, I can't remember if they were every other Friday, right? Members night followed by the special speakers night. And I just wanted you to know that at least, I don't know, 50 to 70% of the members night, I didn't understand a thing. But here I am, and I'm here to tell you about TESS. Now, you may not be able to see the slides very well, but that's fine. I'll still just speak about it, and you can ask me questions towards the end, or any clarifying questions throughout. So I had three things I was going to tell you. What is an exoplanet? I'm assuming everyone knows that. Why the transit technique, the way we found most planets, is so popular. And with those two introductory things, then I'll get to TESS itself. So I'm assuming everyone here knows what an exoplanet is, but in case you came as someone's guest and you might not have known, the point I just wanted to start out by reminding you is that every star in the sky is a sun. And just like our sun has planets, we don't have evidence for sure, but we speculate that almost every single star has exoplanets. And that's what we call exoplanets, a planet that orbits a star other than the sun. Right now, astronomers have found thousands. But as you may know, our Milky Way galaxy has hundreds of billions of stars. So there's probably hundreds of billions of planets here. And so far we've found thousands, but we know there are billions and billions of them. So the transit technique, well, I don't know if you can read the slides here, but what it says is that let's think about our own Earth for a moment. And our Earth, it seems really big, at least if you want to travel, like to see the TESS launch, it's pretty far away. But our Earth is just tiny compared to our sun. Our Earth is 100 times smaller, or 10,000 times smaller in area than our sun. But our Earth is 300,000 times less massive. And in terms of reflected light, if sun is shining and Earth is shining in reflected light, our Earth is 10 billion times fainter than the sun. So if your job was to go out and find planets, which technique would you choose? One that involves area, because our Earth is 1 part in 10,000 smaller than our sun. Some people are nodding. Would you choose something that involves the planet mass, because our Earth is 300,000 times less massive? That's harder. Or would you choose the 1 in 10 billion? Well, the kids are saying yes, the 1 part in 10 billion, because it's going to take that long to figure out how to study Earth in reflected light, maybe. Well, it's easiest to find planets in transit because of this area ratio is the kind of biggest kind of ratio for the planet compared to the star. And that's one of the main reasons that transits are so popular. And I have this little animation, not sure if you can see it. Can anyone see it? Oh, you can, okay. Well, you can see the planet going in front of the star. And can you even see that little planet? Because that's supposed to be Earth size. You've got good eyesight or something. But what astronomers measure, of course, is just that little tiny drop in brightness, measuring the star as a function of time. And when the planet goes in front of the star, it drops by a tiny, tiny amount. And that Earth is only dropping by 1 part in 10,000. Now, a bigger planet like Jupiter will drop by 1%. So have any of you here measured a transit with your telescope if you have like a really great CCD and software? Okay, well, there's something for you to aspire to. It's not a maker project per se, but I have a couple notes here. One is that NASA's Kepler Space Telescope, looked at one part of the sky for 4 years, and it found thousands of planets. I don't know how many of you read the news, but I just read in the news this morning that Kepler is running out of fuel now, and it's in this kind of secondary. It's kind of like in this reincarnated version called K2, where it stares at for 80 days at each patch of the sky that it can look at. It might only have one more patch to go, actually. They're going to wait and see, put it into like a safe mode, like a hibernation, until they can downlink the data, and then wait to see if they have enough fuel to do a final observing campaign. The other note that I have to remind myself to tell you is it turns out that like last fall, Charles and I visited St. Mary's University in Halifax, and they have a nice, I think it's a 24-inch. I can't remember how big it was, 24-inch. But they have this really interesting computer setup. It's a little too easy because you can tweet a planet name to the telescope, and it will know what time to observe a transit of a star in the sky. However, you'll have to have done it manually for a semester before you're allowed to do the electronic thing. Well, but what's really interesting is they have a setup where their telescope and their camera are good enough to observe a transit. And pretty much every single night, at least in the Northern Hemisphere, there is a bright star with a transiting planet. And so if you were to be able to be a college student today at a place like St. Mary's or a bunch of other places around North America, probably the world, you could actually measure transit light curves like this and learn the physics and math to be able to extract the size of the planet and other things about its orbit. So transits are very popular now. The other reason, in addition to this area ratio, is that with transits, we look at a whole, all visible wavelengths. We get as many photons as possible. So when you looked at the sun today, that was H alpha, I believe. That's a very, very narrow. That's the opposite. Our sun is so bright in our telescope, your eye would burn and you wouldn't be able to see all the special features. But in this case, we want as many photons as possible. And so being able to do that, plus the area ratio, that's why transits are so popular. So now, I'm actually also going to talk about TRAPPIST. I don't know if it's your favorite system, but it is certainly one that all people who give talks talk about TRAPPIST. But there's one other reason why transits are so popular. And here, can you see that now? Can you still get it? I can't see from this angle. You can't really see it. Well, what it's supposed to show you is the Earth in front of a real image of our sun, but it's a fake Earth. And it shows you a little tiny star, TRAPPIST. Okay. It shows you the same fake planet around what would be TRAPPIST. And you can see that TRAPPIST is so small compared to our sun. And just a little story about these Belgian astronomers, because in astronomy, like we all know each other, like all the astronomers. So it turns out that Michael Guillon, who we heard about, he set out to study the smallest, coldest stars. They're so small and cold, any smaller and colder, they wouldn't be stars. They wouldn't be able to fuse hydrogen in their cores. Now, his pilot project looked at 20. And can you believe how lucky he was? He found the TRAPPIST system with 7 planets, he and the team. Yeah, and exoplanets were just lucky. They're everywhere. They're bountiful. They keep giving. So it's pretty amazing, right? Like usually you don't get that lucky that easily. But those, in astronomy, we kind of joke about it. We call it the race to the bottom. People always want to look at the smallest stars because that drop in brightness for an Earth-sized planet is no longer 1 part in 10,000. For TRAPPIST, it's only 1 part in 100. And that's much more doable, although your telescope probably still can't do it because the star itself is so faint in the visible. Okay, so I have a few more things about, I'm going to skip that one about TRAPPIST. And because these small stars are so popular in astronomy now, I'll say like a large fraction of professional astronomers have almost abandoned sun-like stars and are fixated on these small red dwarf stars because it's much easier to find planets around them. So what I want to do right now is take you on a virtual trip to a planet orbiting an M dwarf star. Now, many of them that are under study are much bigger than TRAPPIST because TRAPPIST is only 10% the size of our sun. Many of them are more like 20% or 50% the size of our sun. But imagine if we could get in a spacecraft and go to a planet, one in the so-called habitable zone, where as heated by the star, a planet with a thin atmosphere would be not too hot, not too cold, but just right for life. The first thing we might see, depending on the system, is the sun or the star could be very big in the sky. And here, if you can see this one, it's really giant. It's taking up a huge fraction of the sky. The artist here, not sure if you can see it, did an artist conception, used the artist license to make the sky red with purple clouds. There's no real reason for that, just for fun. also showing some other planets in the same system. But what's really interesting about these planets around the small M-dwarf stars is they're very close to the star if they're to be in the star's habitable zone, because the small star gives off very, very little energy. It's like standing next to a tiny fire. To stay warm, you'd have to be very close to it. But because of tides, tidal interaction of the planet and star over even just millions of years, we think that in almost every case, with a few exceptions, the planet will be what we call tidally locked. It will rotate one time for every time it orbits. This is like the moon does to the Earth. The moon shows the same face to the Earth at all times. You know, when you see the full moon, it's not actually, there's a libration going on, so you see a little more than the full half of it. But it turns out that we think that these planets have one side that's permanent daytime and one side that's permanent nighttime. Now, if we could visit this planet in our spaceship on our virtual trip, you could choose where to go. Would you go where it's always daytime? Or, no, because you're astronomers. You choose to go where it's night. But he doesn't like the cold. However, just like when you open your front door on a cold winter's day, what happens? The warm air rushes out, the cold air rushes in. We think as long as the atmosphere is not too thin, like if it's more massive than Mars's atmosphere, there should be atmospheric circulation going around. So it might be kind of cold, but you wouldn't have to worry about like completely freezing. Hopefully, anyway. Okay. Or you could always go, so you could go, or you could go to the side where the sun is always setting. And Charles and I would go to where the green flash is on all the time now. Okay, actually, I told this once at a professional meeting, and someone was furious after and said, it's definitely not like that because it's not going to be perfectly, rotating. And our moon, in fact, if you were to take a picture of it every time at full moon, you'll see a little more, it's just turned a tiny bit this way or a tiny bit that way. So it wouldn't always be constantly the green flash, okay? I mean, I haven't worked this out for myself, but just so you have all the details. Now, these planets close to the star, because of Kepler's third law, they actually go around really quickly. The TRAPPIST planets only have a few day period orbit. That's their year. And this example here, this picture was made for one that has about a 15-day period orbit. That means that would be once a year. So you'd be having this annual event every 15 days. Or for your birthday, for the kids, your birthday would be every 15 days. But that wouldn't be so good for your parents, right? Because they wouldn't do it that way. They'd probably have a different counting scheme. Now, on the other hand, it might not be such a good idea to visit these planets around M-dwarf stars because of flares. These M-dwarf stars flare a lot. And you wouldn't be able to just flip out your phone because electronic, high-energy particles getting blasted from the star to the planet would knock out your electronics. You'd get a worse sunburn than some of you have now. I don't know what kind of sunscreen you'd use, or your DNA would get damaged. We're really not sure. And I say that jokingly, but honestly, the Kepler Space Telescope, in one of its 80-day observations, it did see TRAPPIST. And in 80 days, someone counted 40 flares. And one of these flares, they said, but these flares are happening at visible, in Kepler, it's viewing at visible wavelengths, whereas the flares give out most of their energy at much higher energies, like ultraviolet, extreme ultraviolet, even X-ray. We don't see that, but they extrapolated out, and they said that one of those flares appears to have as much energy as the Carrington event. How many of you have heard of the Carrington event? So some of you have. Well, the Carrington event was from 1850 when a British astronomer, an amateur astronomer, kind of quasi-professional, was studying sunspots and saw one of them whiten just a little bit. And within a day and a half, our Earth was just bright with northern lights. Apparently around here, you would have been able to read outside by the northern lights. And they were seen almost as far as the equator. At the time, we didn't have, we or they or whoever had telegraphs. And they found even taking out the batteries, the telegraph still worked. And some people even got their hands burned. And what happened was a small part of our sun came off in a flare, a coronal mass ejection, came whizzing right towards Earth, and it had a little magnetic field embedded. And when it interacted with our magnetic field, it essentially lit up our Earth, electrified it. And this was bad, actually. And you could be worried. Some people look worried. You should be worried because if this happens today, some parts of the world, I'm thinking of the US, will be in big trouble because the power grid will just be completely damaged. Here in the, I'm not sure who remembers in 1987 where, yeah, Quebec, and they had this kind of mini version. But now there's essentially the equivalent of circuit breakers, so we're safe here. But the point is that we're really not sure about these TRAPPIST planets or about M-dwarf stars, and there's still a big debate in the community. Would you really want to visit this planet? Do you think it's a good place for life? I mean, I've given a very biased view just to sort of shake it up a little. But we have this feeling in astronomy where we just have to look at what's easiest to do. We're doing the easiest things first. I think that's only human nature. So that's where we're at right now. And that's the story about TRAPPIST. We don't know, even if they have atmospheres. Some people speculate that the star's wind and high energy particles have eroded the atmosphere, so it's gone completely. And we really don't know what is out there. But that's why astronomy, it's a true journey of exploration. So now I'm going to turn to TESS, Transiting Exoplanet Survey Satellite. And I'll tell you about TESS, but before I do, its kind of highlight is to find planets around small M-dwarf stars. Because remember, it's easy. We can look at all photons at visible wavelengths and get a good signal. And they have short periods, so you can see them go around every 15 days or less. And that's what we need. We need to see more than one transit to be sure of what we found. So TESS is, now I have it's an MIT-led NASA mission. It's an all-sky survey to find planets with the transit technique. It's run by a lot of different groups. MIT, it's sponsored by NASA, but NASA Ames and Goddard Space Flight Center have a leading role. Orbital STK, now Northrop Grumman, built the satellite bus. Harvard Smithsonian helps with follow-up. And George Ricker is the PI. We have we have to give everyone credit, so I should have spent a lot more time on that part. But I'm going to go through a few different things now. Why TESS? The TESS cameras and spacecraft, the orbit and sky coverage, launch, orbit, and sky coverage, data, and follow-up. So now, the thing in exoplanets. Who knows the current count of how many exoplanets we have? No one? Oh, good.
Around 3,000.
Around 3,000 something, yeah. It could be around 3,700. And they're divided into ones that are kind of confirmed, where we have a mass, or kind of validated, where we don't have a mass, but we're extremely confident they're planets. Now, out of all those planets, we don't know a lot about most of them, actually. We might know their size and their orbit, maybe their mass. We'd like to learn a lot more. But many of the Kepler planets, for example, we can't learn anymore because the stars are relatively faint. They're like magnitude 11 would be bright, more like 15. We want very bright stars where we can have lots of photons. We can study the planet's atmosphere and measure its mass and do a lot of follow-up that require way more photons than we have. So we want to find planets around very nearby stars. I have this little animation which is zooming away from Earth. That circle is 3 parsecs. It goes out to 10 parsecs. It's going out to 30 parsecs. And it's showing you the stars with transiting planets. Blue is Kepler. Now these Kepler planets are all, this doesn't have K2 by the way, but the Kepler ones, they're mostly in one direction because Kepler was just pointed in one direction for 4 years. So that's kind of what we have now. And this next animation shows the same thing, but yellow is predicted TESS. So as we zoom away from Earth in these concentric circles, I want you to look at the difference between the yellow stars highlighted on this map and the blue ones. Of course, we haven't found the TESS ones yet, so this is just a simulation. And the blue ones you can see as well. So see the difference. The Kepler stars with planets are largely out at thousands of light years. TESS will be, let's say, hundreds of light years, which is still incredibly far away, but hundreds still sounds better than thousands.
Basically, the stellar neighborhood.
Well, there's even closer stars, as you know, like Alpha Centauri at a few parsecs. And there's lots of stars within. I mean, some people want to go even closer, actually. But I'm here to talk about TESS so we can compare in Q&A. Here's another figure showing you brightness now, because, you know, brightness and distance are related for main sequence stars. And this is showing you blue is Kepler planets, green is other. And this is showing you TESS, where this is stellar magnitude, so the brighter stars are on the top of the diagram. If you can read this, you can see it says naked eye. I don't know here who can see 6 magnitude naked eye. You can? Contacts? Wow.
Well, with my corrective lenses.
Corrective lenses, yeah. I guess in maybe a really, really dark sky. I don't know, I've been always skeptical of that statement, that you can see magnitude 6. But So that's naked eyes up there. Then it shows you binoculars, magnitude of 8 and brighter, telescope. So you see the Kepler stars are quite faint. They're all pushed to the bottom of this diagram. But the TESS ones are a lot brighter. And that's the motivation for TESS, is to look all around the sky and find planets around bright stars. Also, just a little more technical thing, the James Webb Space Telescope, every astronomer pretty much is banking on this one to do great things. And in exoplanets, we're hoping to study atmospheres of exoplanets, transiting exoplanets. So we have a joke where we call TESS our finder scope. So TESS is going to find all the planets, and we're going to spend years and hundreds of people working on them to find the very, very most choice planets to follow up their atmospheres and learn more. So now I'll tell you a bit more about the TESS spacecraft and cameras. And each of these is pretty short, by the way. So here's a picture. I hope you can see this one. This is from, I think this must have been like January or February. And this is at Orbital STK, now Northrop Grumman, in Virginia, USA. And you can see two people wearing these bunny suits. It's in a clean room so that dust won't get onto the TESS spacecraft. And you can see it's not very big. It's about, I want to say about 5.5 feet tall. You can see the solar panels. You can see a radio dish to communicate with. And you can see 4 giant things inside. Those are the cameras with giant baffles. And there's covers on them in this picture, but those were taken off before launch. So TESS was good. It had no deployables, because deployables are worried because they might get stuck. And if it doesn't, just like the parachutes today, remember? You're like worried they're not going to open. Yeah. So it only had the solar panels were the only thing that folded up and came out. Okay. So here's just a schematic picture of the TESS camera. There's 4 identical cameras. This is showing you on the left a giant lens hood or baffle. And you see those ribs in between? It's so light comes in from the moon or the earth. It isn't supposed to get into the camera itself. So it's to block out the light so we can spend more time observing. Or less time, rather, there will be less time when the detectors are blinded by light. It has 7 lenses. It's like a custom-made camera. It's got this lens assembly. And at the bottom, there's a detector assembly. So the aperture of the cameras isn't very big. It's about 10 centimeters in diameter, which is kind of about like that. When you think of space telescopes, I bet you think of like giant mirror. But remember, TESS is searching bright stars. So small aperture is good enough, actually. Let's see. Okay, so it's got a big field of view. We'll come back to that. 16 megapixel camera with 21 arcsecond pixels. I just put that in case you're interested in the details. But those pixels are really big on the sky, unfortunately. So oftentimes a bunch of stars will be on a pixel, and we won't necessarily resolve all of them. Here's a picture of one of the detectors. It's a CCD. What's most interesting for astronomy is it has a wide spectral bandpass, letting in light from 600 to 1,000 nanometers. I'm going to talk about the launch, orbit, and sky coverage. How many people here were at the launch? We actually, several people. It looks like there's about 6 or 7. Okay. So the launch was really exciting. I have a little movie of it that Charles kindly got me. And it will just have a countdown to try to capture the excitement.
9,
That's the
8,
SpaceX
7,
Falcon 9 rocket on the
6,
launch pad.
5, 4, 3, 2, 1. Ignition. Liftoff.
We were all about 6 miles away, but that plume was so bright. I mean, it's bright there and that. I mean, it's a bright day out here, but it was unbelievable, and everyone was so excited. The launch was delayed many, many times over the last couple of years, but there it went off perfectly, and it was just absolutely brilliant. You have to wait, because once it launches, you think it's all set. It's not, but the stages have to separate, and a lot has to happen, but it did a great job. SpaceX did a fantastic job. Actually, it was supposed to launch one day, and then they delayed it. We were on these buses that take you to the actual viewing site, and just as our bus pulled into the parking lot, we were told that it wasn't going to go that day. And so we had to go back, wait a couple days, and then the launch went off. And people have, the whole project was over 10 years from concept to launch.
And it's fairing.
So here it is.
Now coming up in about 15 minutes, you're going to hear the call out that Falcon.
So I have another little video clip I
TESS,
wanted to show you as well,
the
which shows you the
Transiting
really
Exoplanet
interesting
Survey
orbit of TESS, because it has a unique orbit,
NASA's
which is
newest
the first time it's
exoplanet
ever
mission.
been used.
Led
It
by
shows you a couple
MIT,
of beauty pictures
TESS will
first,
find
and then it will get to the
thousands
orbit.
of new planets orbiting nearby stars. To accomplish this, TESS will fly in a special highly elliptical orbit that maximizes the amount of sky the spacecraft can image. Once TESS has launched, it will expand its orbit until it can get a gravitational assist from the Moon. This slingshot will move it into a stable orbit that is tipped at about 40 degrees from the Moon's orbital plane. TESS orbits Earth in exactly half the time it takes the Moon to orbit once. This feature helps stabilize the spacecraft's orbit against tugs from the Moon's gravity. TESS will spend most of its 13.7-day orbit observing the sky. As it approaches Earth, TESS will rotate and transmit all its accumulated data to scientists on the ground. Over 2 years, this will allow TESS to study nearly the entire sky and potentially find thousands of new exoplanets.
Well, in case you weren't remembering it, the International Space Station and the Hubble Space Telescope, they're in low Earth orbit, and they're orbiting Earth every 90 minutes, actually. So if TESS is taking 2 weeks to orbit Earth, that's a huge orbit. And the reason why TESS wanted to go in this unique orbit was because Earth is really bad for astronomy. I mean, you've noticed, right? Daytime and clouds. And Earth's bright and hot, and that gets back into the spacecraft. Like when Hubble orbits Earth, you know, it goes in daylight and it expands a little bit. Goes in night and contracts. That's bad for transits, for high precision measurements. It's not good to have it. You know when you can't open the jar and you run it under hot water and then the lid expands and then you can, yeah, it's like that. You don't want that. So it's in this orbit where most of the time it's far away from Earth, orbiting very slowly. And based on Kepler's law, it zips around the Earth when it's close, downlinks its data, then goes back to orbit. And TESS will have this pattern on the sky where it's doing one giant strip of the sky. Each of the 4 cameras points in a slightly different direction, so it covers a giant strip where every camera takes up 24 by 24 square degrees. So I'm going to tell you a bit about the data. This is simulated data, but this whole thing is 1 square degree patch of sky showing here. Does anyone know what a square degree is? Like you stick out your hand, I think it's like a finger. That's a degree, so that's what this picture is, okay? 1 degree on the sky. But look in the top right there, that was 1 degree. This is 1 detector, 12 degrees by 12 degrees. But not only that, each camera has 4 detectors. So now, can you still see in the little right corner there? That's actually 1 camera alone. It's 24 by 24 square degrees. And that would encompass the constellation Orion. And there's 4 cameras. So every, TESS observation is taking up a huge part of the sky. And you might have, okay, this doesn't do it justice. You can look this up later if you haven't seen it. But TESS has a beauty image. They released a JPEG. It wasn't like a real FITS file or something astronomers can really use, but just to show how great the cameras are doing. This is showing you, and this is just a tiny patch of the sky. It's 3/4 of 1 detector. So it's just a small part. And this is the Coalsack Nebula. I don't know if you can see, there's so many beautiful stars here. The bottom left, you'll see, that's not diffraction spike. That's when the star is so bright, the detector saturates and it gets this little blooming effect. So the data, and I'm going to go, this might get a little technical for some of you, but others of you will like it, so I wanted to include it. And this is the TESS data, what data we're going to get down. This one is showing you a little patch of the sky. This is, TESS actually takes 2-second exposures. They're used for guiding the telescope, but it's not suitable for downlink because we can't downlink all the data we get. It's just like if you're somewhere where the internet is really slow, you just can't get all your information down. In this case, TESS downlinks on the Deep Space Network, 3 giant dishes spread around the Earth, and they're shared by other NASA missions, so we can't downlink everything. So instead, the data is binned on board, and there's several different categories. It's binned to 20 seconds, but only for little postage stamps. So it's like as if you're astroimaging with a beautiful image, but you can only get little blocks cut out all around. So stars, there's a huge amount of work that went into making this TESS input catalog and which stars get special treatment. So a very small number get this 20-second treatment. Most of them, the best ones, 200,000 stars spread out over the mission, get the 2-minute cadence. So that means even though it's taken like every few seconds, it's added together on board, so you get 30 minutes. It's like as if you're taking a movie here, but you only can get 2-minute like shots from the movie. And then finally, the full frame image, the entire camera, all that stuff will be added together every 30 minutes. You can get all of that too. So these products will all be made public eventually. If you're interested or have any inclination in learning about it, that's what will happen. So the last part of my talk and the last part about TESS is about follow-up. So what happens is this, that TESS is taking all this data and it comes down to Earth through the Deep Space Network. It comes to MIT. Some of it, we send it to NASA as well. And we look for planets. And it's kind of crazy to say now, but finding planets with transits, it's more like standard actually. It's their sort of protocol that's been really well developed. And people have honed all their skills and their computer code on Kepler actually. And there's people who do various different things, but it all has kind of the same underlying way to do it. So even though we'll be looking at these 200,000 prime planet stars and probably millions of more, at the end of the day, the TESS goal out of millions of stars or hundreds of thousands is to come up with 50 planets. 50 planets that are small with measured masses. And so there's actually a giant effort that is happening. This is kind of what I do for my day job though. I was going to say unfortunately, but is I have to organize the MIT team to find planets. And we do this, this might really surprise you, but I just wanted you to know it's not all done by computer actually. We use the computer to find the drops in brightness that might look like a transit. But we have an extensive human vetting internal to MIT and with some other team members. Humans look at every one of them and a bunch of associated data products to say yes or no actually. Because it turns out that some of the best ones, the most promising, the smallest planets, the data looks really horrible because they're these tiny drops in brightness and it's quite messy. And our human eye still is better and more efficient actually than computer programs. Now, if you're a real programmer, I know you'll disagree with me. So we're also doing what Kepler did later in its mission called auto vetting. So the same data products, the computer can also sort through. And hopefully the computer eventually will be able to do as well. But you know, when you don't only have, right, 200,000 light curves, 20,000 per month, you don't want to miss anything. Like how would you feel if it was your job to find these 50 planets and you messed up and missed half of them, half of the best ones, because you said, well, my computer can just do it for me. We do other more sophisticated things you can ask about. People try machine learning. There's reasons why it doesn't work that well for finding planets, mostly because we don't have a good enough training set for it. But we can get into that. But I just wanted you to know that just TESS itself and the launch and everything, that was just the first part. Even finding the planet transit signals is only the first part. And there's a giant follow-up team that has basically people from all around the world. I'd say there's like 100 people involved and dozens of institutions in probably 20 countries. So I may not go into the detail on it because it's kind of detailed. What I'll do is I'll summarize and then we'll have time for questions. Okay, so those of you interested in exoplanets, I bet you read about it a lot in the news. But usually it's a new planet or some study that's actually most of it's wrong, unfortunately. A new study saying that they found water or signs of life, or there might be a planet that can have life. But I just want you to know that exoplanet science began as a single planet discovery and study. And in some ways, we're still there right now. Kepler enabled it for big data, finding thousands of planets. But we know very little about the planets individually. We might know their size or their mass and orbit, but not much more. So the goal for TESS really is to enable what we call ensemble science, that you can have groups of planets. For example, you could have planets around these small M-dwarf stars, and you could ask yourself, if the star flares a lot, does the planet still have an atmosphere? So we'll be able to attack questions where we need to have lots of planets and lots of detailed follow-up measurements because the stars will be so bright. Now, if you want to help find planets, you can go to planethunters.org. Have any of you tried this? The thing with planethunters.org is it takes data from Kepler and it's crowdsourcing it. And so what I told you is we're at MIT, we're going to do human vetting. Part of it is just like Planet Hunters, actually, where you're just scrolling through light curves once you do a tutorial, looking for little drops in brightness. When I've done Planet Hunters, I was a little disappointed because all I found were injected fake signals because they want to make sure that as a user, you know what you're doing, right? Like they have to calibrate you somehow and make sure that you can find the fake stuff. Because if you don't find the fake stuff, they can't really trust it when you say you found a planet. But I do encourage you to go there to this website and fool around and learn a little more about planet finding with transits. I have one other thing that I think you should go home and do and download this software. It's called Eyes on Exoplanets. And you need to have enough bandwidth to download the program, but it's amazing because they have a real map of the stars and you can like pick any point on Earth and see what your night sky is that night, and it'll show you which stars have planets. And you can just do naked eye if you have good eyesight and can see down to 6th magnitude, or it'll show you all stars down to any magnitude, and you'll just see how many stars with planets there are and which stars in your night sky. Although you wouldn't be able to see the planets themselves, you could just know that the stars out there have them. You can also click on the star and learn more about the planet. So just to summarize, TESS and exoplanets. Thousands of exoplanets are known to orbit nearby stars. Most information is limited to their sizes, masses, and orbits. To learn more, we need lots of planets orbiting bright stars. That's the takeaway. So TESS is going to find a lot of planets, thousands of them, even 10,000 maybe, orbiting bright stars. TESS is specially designed to search nearly the whole sky for exoplanets with 1-month periods transiting bright stars. And it's sensitive. Don't forget the message, the take-home message about those small M-dwarf stars and how they're kind of crazy because they have a lot of flares. They're the easiest thing to look for. So that is where our search is headed right now. Thank you. Okay, so while we wait for questions, I'm assuming someone would ask what's the status update, so I'll give it to you. So TESS has not started its science phase yet. It was supposed to have a 2-month commissioning. That's where you turn everything on. It's like waking a person up from a coma. You don't wake them up and say, okay, go run the Boston Marathon. You say, wake them up, hello, are you there? Put them back to sleep. Maybe the next day, can you sit up? It takes a long time to sort of try everything out one by one before you can try it all together. So that all went extremely well. A couple of there's always expected glitches. That's all going well. But TESS is still working on its pointing right now. It's fine pointing specifically. I can't say more. I'm actually on kind of on vacation now at my in Charles's summer cottage. So I'm not in on the latest. But TESS will start its science observations soon. And then it takes 1 month for each strip of the sky. Remember, it's doing 2 orbits on each strip, and it will downlink the data after that. But it will be probably a while before you hear any news, actually, because NASA wants to keep quality control. We can't just blab all the great things we hope to find right away in the TESS data. So it might be a few months before you hear anything, but it might be sooner as well. But I think once TESS does start its official science operation, that NASA will most likely make an announcement, so you'll know when that's happening. Any questions?
Hi. So you were saying that TESS is going to do onboard data crunching before it downloads it to Earth?
It's going to compress the data. It's going to bin the data on board, yeah.
Okay. Are you going to be distinguishing variable stars from exoplanets
Okay,
before you...
right. So TESS won't be doing anything clever on board. It won't be doing any data crunching per se. It's simply going to stack images together.
Okay.
It will remove cosmic ray hits. That's the only kind of intelligent thing it will do. Everything else comes down to Earth, and we look for everything there. And the TESS team is quite broad. There are people, anything you name, they'll be doing. So variable stars, yes.
Okay. Thank you.
If candidates planets identified, what would be the immediate follow-up? Or are you waiting for James Webb?
Good question. So the question is, what will be the follow-up when we find planet candidates? There's actually 6 different follow-up groups. I'm not going to bore you with the details. And one of them is called reconnaissance, actually spectra. Take a spectrum of the star and make sure it's the type of star you think you were looking at. For example, what if it was a red giant instead of a red dwarf? Then the object that was creating the transit is probably a star and not a planet. Believe it or not, some of the reconnaissance are just ground-based visible wavelength telescopes that would be 1 to 2 meter in size to look at the transit and might be able to do a better job than TESS's tiny cameras, tiny apertures. So there's several follow-up just to identify it as being a planet candidate. And then the main thing TESS is going to do is get the planet mass. So there's a different technique called rate of velocity. The planet and star orbit the common center of mass, and the star is actually wobbling. We measure the line of sight to get the planet mass. So that's kind of the key follow-up thing, is the planet mass. And with the mass and size, we have density. And then we have like this pristine high-value catalog where we'll use the James Webb, earlier on Hubble, and other things like that. Yes, we have a question here in front. We'll take Eric first, then we'll go over here.
This is a question that may also apply to TRAPPIST-1 when there are 7 different planets and they all are in a resonance with each other. The one that I'm familiar with is with the moons of Jupiter, Io, Europa, and Ganymede. And for every 4 times that Io goes around, Ganymede goes around once, I think. And these resonances can be a lot like trying to slosh bath water out of a tub. And if you're moving at the same speed that the water is sloshing back and forth, it can end up being totally sloshed out. But these planet systems with up to like 7 planets, there could be a lot of sort of slosh in there. So I'm wondering
Absolutely.
about the forces that can stop them from just
Yeah,
thrown
and
away.
actually TRAPPIST is a perfect example. First they found, I think, 2 planets, but the 2 were actually 3. And then they used a different telescope, the Spitzer Space Telescope, and they found that there were 7. So it'll be like that. Like we'll find something interesting, but the objects will be farmed out to various people, astronomers, who will study them in more detail. So the bottom line is that we'll see a transit and we'll have to do a lot more work to uncover everything there. However, the question is very interesting, and that's precisely why we don't just trust the computers. It's most likely that via planethunters.org or just, let's say, undergraduate students, we'll look at every light curve. We can't look at millions of them, but we'll just check them all out to make sure there isn't something that got thrown out. For example, one of the data products that we use to tell if it's a planet or a binary star, like if you have an eclipsing binary, 2 stars going in front of each other, you'll often see 2 transits, right? One star goes in front of one star, then that star goes in front of the other star. And usually they're different sizes. So you'll have one transit, and then the next transit would be deeper, let's say. So you'd have odd and even transits would look different. So one of the tests so it's possible, what Eric is saying is that you could throw something out because it didn't pass your test because you were looking at something. So certainly things might get thrown out, but we're going to try to have, a search through the trash kind of subgroup.
They get thrown out of the system.
Oh, you meant the planets are going to thrown out. Okay.
Getting planets ejected.
Well, okay, so what's your question? How will we know, or?
What's the likelihood of an exoplanet?
Okay, he had a different question.
I guess,
than the one
I guess the
answered, so.
planet is, what's the likelihood of a complex exoplanet system, when there are 9 in the bed and the little one says roll over and one of them gets thrown away?
The question, yeah.
Or do these resonances help to reinforce the stability of the system?
All right, so there's several questions in there, but let me just say that some people think every star system has kicked out at least 1 planet, probably more. And the analogy is not so much the resonance systems, but that, like our own solar system, is gravitationally full. If you tried to stick another planet in, the whole thing would go haywire. It's the analogy of the coffee cup analogy, that imagine if you walk in a restaurant and every coffee cup is just perfectly full to the brim. Do you think there was just a really good waiter who he or she could fill it up perfectly? Mm-hmm. Or would it be easier if someone just overfilled all of them and the coffee outside evaporated and you just had these perfectly full cups? Well, the theory is like that if every solar system every planetary system where we can find every planet there, they're all full. All of them appear to be dynamically full, so there should be ones that were kicked out. That's what we think anyway. Now, the resonant ones are something else. And just to add to the complexity, most of them, I'm not sure about the TRAPPIST-1 system, so that can be your homework assignment. They're actually just out of resonance. So instead of being a perfect, like, one goes around once, another one goes around twice, another one goes around 4 times. That would be like 1, 1.9, 3.9. Most of them that are in resonance are just outside, like something prevented them from getting right into resonance. And so that's a really one of the kind of like top 10 mysteries that people haven't figured out. The resonance we think isn't related to planets being expelled, but some people think it's related to them migrating. But honestly, your idea would be as good as anyone else's at this point because we're not really sure.
The Kepler telescope was expected to live 3.5 years, but it actually ended up right now 9 years. So the TESS is expected to live 2 years. But what are your expectations of how much do you think it'll?
Yes, so
last?
There's a bunch of answers there. Most spacecraft live way longer, actually. And it just, unfortunately, I hate to have to explain it to you, but it's mostly money and politics. But essentially, when you want to propose to do a mission, you have a great idea and you put it forward and it takes a long time, but when it succeeds, TESS has a 2-year prime mission phase. So that's there's money to run it for 2 years. But they will be they will be asking for more time. And TESS itself doesn't have, it's in this very stable orbit with the moon. So it's orbiting in this crazy high inclination, very elliptical orbit. but stabilized by the moon, so it doesn't have to expend much fuel, actually. So as long as all the parts keep working, like the batteries work and the reaction wheels work, as long as nothing fails in it, it could live for decades, actually. Like, think of our Voyager spacecraft. You know, parts of them are still working after 30 years. And so the other little thing, sort of secret or not secret, is that every engineer wants to hold margin. So if you tell someone you have to build it this well, on a scale of, you know, out of 10, let's say you build it to a 9, they'll want to build it to a 10 or an 11. And so if everyone does that, no one wants to be the one to blame that your system failed. So it tends to, like, think about the Mars rovers, not Curiosity, but the twin rovers. They're supposed to last 1 Martian year, and they last like a decade. So TESS could potentially, its orbit will be stable for decades, and it could last indefinitely. Okay, if there are no further questions, I'll be around, so thank you again.
Okay, well, thank you very much, Sarah, for a fascinating talk. It's always nice to find out what you do, and it has been a very informative time. So in appreciation, we'd like to give you this little package to say thank you for a great talk.
Thanks so much. Thank you all.